Is this voice from your side, Raghavendra?
No, no, not from my side.
No?
Not from my side, no.
Okay, let me check
To
then.
make me bright and smart. Eh,
Raghavendra,
clip
you have
it
logged in from
here.
two accounts, I think.
Oh, sorry.
Clip
I had.
it
No, ma'am, I only have one tab open right
here.
now.
One
I'm
tab
only logged
open.
in using.
Okay.
Clip
Yeah,
it
please, I
there.
request the participants to mute your mics. Yes, Raghavendra, please continue.
Okay. Yeah. Sorry about that.
Yeah, it's
Okay,
okay.
I'll continue. Yeah. So that is why we do this. I think I left off at the point why we do intersample interference and that we select this, right? How we select how a Nyquist. Okay, so I'll just recap this quickly. A Nyquist pulse is something that goes from -infinity to infinity. It's a mathematical concept, but we really can't make this as a practical scenario because infinites are in real world is not possible. So what we do is we instead take a finite signal, which we called as a raised cosine pulse RCP, and the pulse on the frequency domain, it doesn't look like an exact square. It's similar to a square. You have a little bit of a little bit of sliding over here. You have a small amount of angle that's present, but that's okay because you're not actually going beyond the limit that is set for you. So that is what we do. We shape our pulses, we shape our signal in that format so that one, it's intersymbol interference doesn't happen, and two, we don't go beyond the limit that is set for us. So perfect roll-off is in the case of a Nyquist pulse. We do the same thing for a raised cosine pulse, except that we give something called as a roll-off factor. So roll-off factor is basically how well your frequency domain signal looks, how close it looks to a square. The higher the value of the beta, the higher it goes, the lesser it looks like a square, the lesser it looks is close to perfect, and the smaller it is, the more it looks perfect. Usually, we select a beta value of zero point 0.5. This is also sometimes called as alpha. It's the roll-off factor. So sometimes, typically, we choose this as zero point 0.5 because that gives us something which is not too big in the time domain, and it is pretty close to an ideal value in the frequency domain. Now, this is the last concept of where we don't typically use raised cosine pulse, but we use something called as a root raised cosine. A root raised cosine looks, the roll-off looks very, very similar, and the time domain signal also looks very, very similar to that of a raised cosine, except that the difference is that in the frequency domain, you take the root of the raised cosine and then use this as the transfer function in order to obtain your signal. So you send a pulse like this, you obtain something like this, and then you do it instead of doing it for the raised cosine, you use the root raised cosine. The reasoning, again, I'm sorry to say this, I know I've been saying this for a lot of concepts, but most of these make sense when you are looking at the receiver. So I'll ask Ajay to address all of these. He'll give you a recap of pulse shaping, and he'll then take you forward to the receiver concepts where you'll understand most of this. In fact, the very first receiver concepts involves why we use the root raised cosine. So this is the end of the transmitter. I will quickly show you the code. I'm sorry, I might be overstepping my time, but I'll quickly show you how we've coded this. So the transmitter front end looks something like this, where here you define all the USRP parameters like device name, accurate, carrier frequency, gain, and antenna. Over here, you have all of the controls over your channel coding. You can, like I said, we do a packetization, right? So we can choose the number of data bits per packet. There is a limit. You can go from 1 data bit per packet to 8192. This we've seen works, this range works pretty well. So we've selected this range. Right now, we have defined two of them having a convolutional, and we have kept a separate blank portion where if anybody wants to do a custom, like one of you asked, LDPC or turbo codes, if you have a custom code that you want to build and place it, you can actually easily place it over here and then execute it. And then you have parameters for each of them. So in Hamming, you have to specify the Hamming order. Convolutional, you have to specify the rate. So 1 by 4 means that you send X number and you get out 4X. And of course, there is your constraint length. And then modulation type, typically we only use three of these because your lower end USRPs will not be able to capture the fine difference between a 16 or a higher QPSK. But if you have a higher end USRP, you'll actually be able to do that as well. And then you have your package structure. So I as a user will be able to define how many guard symbols I want, how many sync symbols I want, how many training symbols I want. And of course, your filter parameters are all over here. And we usually show this for a text input because it takes lesser time to transmit and receive. So we have a poem over here where we'll be able to send and receive a text data. We're also actually almost like 99% we are done with audio and image as well. So I can actually ask Ajay to show you once he's done with the receiver, he can show you a demonstration of how all of this works. And here you can also visualize a lot of aspects of your signal. So you can see the received constellation. You can see the, sorry, this is the transmitted constellation. You can also see the eye diagram, the IQ waveform, and you basically just have a preview of this. And here you have a very simple block diagram. Ma'am, is it okay if I continue for 5 more minutes?
It's okay. It's okay.
Okay. So over here, like I said, LabVIEW is a programming language based on blocks and wires. So basically, if you want to do something like an addition or a subtraction, I have to select a block and then place it. I have to wire the inputs like this to add my signals. I'm just showing you an example over here. So similarly, there are a lot of processes that are involved, a lot of data structures that are involved. You have arrays, you have, so in C you would have come across a concept called as struct, where you'll be able to put in components of many data types. It doesn't have to be the same data type. So in LabVIEW, that same concept is called as a cluster. You can see it over here. So basically, at this point, since you don't have much of LabVIEW training, we just assume that there is a lot of data that is coming in and going out. I'll tell you the important part so that you can understand. So to start off, we use something called as a producer-consumer architecture over here, where you can see this gray color box on the top and a gray color box on the bottom. It's called, one is called as data generation loop and the other one is called as transmission loop. Basically, data is being generated in this loop and simultaneously this loop is also running. There is a data transfer mechanism that we've employed between this loop and this loop where continuously data will be going between, like from the first to the second, that is from the producer to the consumer. We do this so that we get a sense of parallelism in what we're doing and basically the actual USRP. So this one, this loop that you see over here, does all the processes required to send the data from your computer to your USRP. So we don't want this to be disturbed by the actual process that generates my data. Basically my channel encoding, decoding, all of that. I don't want to stop this just because I'm doing that. So we employ a parallel mechanism. So we start off with taking the text input. You see this block over here. This is something called as convert text to bits. So basically we take the ASCII values of the text, we convert them into their bit values, and then you see this blue color wire that's coming out, that is where you get your actual bit data. So it gets converted from A, B, C, D, E to zeros and ones. After that, we do our coding over here. We typically prefer convolutional encoding because it gives us better data output. The faithfulness of your signal is better over here. So after this, we do a packetization over here. We generate packets, meaning we firstly split the data from, if it's 10,000 bits, we split it into bits of like sections of 1,000 because that is what I've defined over here. After that, inside this, if you actually look, we generate your sync bits, your training bits, and your guard bits. And we generate them by simply doing something. There is a function called as empty generate bits that will allow us to generate a PN sequence of a particular order. So for sync bits, we take a slightly different order. For training bits, we take a different order because we want to, the data itself to be different. If you take a PN sequence generator, this is just some extra information I'm giving you. Any PN sequence generator you give, even if you run it 100 times, the output data will be the exact same unless you change the order. So if I take 9 order and then run this 100 times, all the 100 times it will give me the exact same output because it's a pseudo random generator. It's not a true random generator. And that is again a problem in computer science. That's a totally different thing. As far as I know, in a typical system or rather a conventional system, they have not generated a true random signal. There are some quantum computers that are capable of doing this, but let's not get into that. So over here, we generate our sync and training bits. The guard bits are basically just zeros. That's why you see the zero here. We take a bunch of zeros and then just put it in over there. And then we put our data bits as well. Now, after this, we have our actual modulation, or rather, to be more accurate, we convert bits to symbols. So, CSODX map bits to symbols is what we use here. Post that, we do an upsampling process. The reason being that, let's say this is the symbol that I'm supposed to convert into this root raised cosine waveform. Now, in a computer, obviously analog signals are not present. Everything is in either discrete or digital format. If I only have this one symbol, then I can place it only over here. And the rest of these I will not be able to represent. So instead what I do is, and that won't make sense, right? Because if it is like this, the output will still look like this only. But I want this root raised cosine pulse shape if I want to avoid intersymbol interference. So what I do is, I take this one, I append some zeros in the beginning and append some of them at the end. So what happens is this particular symbol, it is then capable of being represented as a root raised cosine. So once I pass it through the root raised cosine this thing function, what happens is it will look like this. Now, although this is discrete, you can say that this somewhat looks like a root raised cosine pulse. You trace this, it will look like a root raised cosine pulse on it. Which is why we add some zeros before and after our samples. Please don't confuse this with the digital up conversion that we do in the USRP. That we do because of the ADC rate. We want to match the ADC rate. Here we do it because we want to get a proper shape for our pulse, which is why we upsample it over here. The usual upsample factor that we keep is 16 because this seems to work very well for us. But you can actually go up to things like 4 and 8 depending on your application and your pulse. So after all of this happens, so all of these are what I explained to you just now. After all of this happens, it gets sent to this loop where this is an something called as a USRP write PX API. So anything that you have, it will take it through, if it yours is a USB channel, it will take it to the USB channel and dump it on the FPGA. If it's an Ethernet channel, then it will go through the Ethernet channel and dump it on the FPGA. You don't have to specify which channel. The APIs are capable of detecting that automatically and then sending it. You don't, as a user, you're actually the USRP APIs are pretty good. They'll be able to handle a lot of things on their own. You don't have to specify so many things. And over here, you have a couple of configuration USRP APIs where you can specify the IQ rate, carrier frequency, gain, and then you get their coerced values. Like I said, carrier frequency you can set to even 10 gigahertz, but if the USRP is not capable, the driver will automatically detect that, and then it will say, I am only capable of putting it to this value, so I'll keep it to this value. So 6 gigahertz is maximum, so I'll keep it to 6 gigahertz, on and so forth. If you so this is basically I'm giving you an overview of the code. I could go deeper, but that would require you to know and understand a lot of LabVIEW concepts, and we're actually running short of time. So anything that I might not have covered, I will tell Ajay. So rest assured, he will give you a more detailed description if you require so during his session. I'm sorry for overshooting my time. Are there any questions up until this point?
Yes, dear participants, if you have any queries, you can put forth here. Yeah, I think the participants are very clear with whatever you have discussed, Raghavendra.
Okay.
Hoping that we'll end
Somebody
this
seems to have a
session.
query.
They have some query?
Yeah, I heard someone else. Yeah. Yeah,
Yes,
please tell
yes.
me.
Yes, sir, please.
Mm-hmm. Yeah, correct. One second, let me go to the code. Right, so right after channel coding, we do the packetization process over here. Correct. Mm-hmm. Not really. So coherence time, you are right, coherence time does come into it picture, but this is something that we will have to predict beforehand and then experiment with. So you're basically talking about channel changing across time, right? That's what you mean by coherence time. Coherence bandwidth and coherence time, right? Right. So that is something that you can think of experimentally for things like 1000 data bits per packet, and it also depends on how fast you're sending data through your USRP. Since we're usually dealing with smaller bandwidths, coherence time is not a problem that we have to address for a small set like 1000. Maybe I gave 10,000 as just an example. That is a very, very small value. Maybe if you're going for a very large amount of data, then you will have to come across and think a lot about coherence time. But if you're talking about small things like 1000 data bits per packet that are actually going at a pretty high accurate, 500 kilo samples per second, then you don't really have to worry about it. And even if you do feel worried about it in your application, whatever you're building, the only way is, or rather, the most practical way is to experiment and see with it, because calculations can only get you so far, and you won't be able to very accurately build a mathematical model for your channel. So the easier way is to just put different values, number of data bits per packet, and then experiment with them. We found that 1000 to 8192, sorry, 0 to 1 to 8192 is a pretty good range. But again, the 8192 limit that we are giving is more towards the USRP hardware's limitation rather than your coherence step. I hope I answered your question. Yeah, sure. Sure. Mm. Yes, this runs on my PC, correct. PC and USRP, so there is actually a protocol that is involved called as DMA FIFO. Okay, I'll just take 1 minute to explain how that works. Your FPGA is actually in charge of communications. Inside your CPU, if you look at it, you have inside your motherboard, you have a CPU, you have something called as a memory controller, you have your actual memory location, and then you have a bus that goes to your FPGA. Right. So when I use this USRP API over here to transmit data, this particular API, what happens is, if you involve your CPU is actually doing a lot of processes in the backend. So if you involve your CPU, the data communication process becomes slower. So what you do is, instead of pinging the CPU, the memory controller directly takes the data from your memory location and then sends it to the FPGA. And depending on your protocol, if it's an Ethernet protocol, then it will follow those standards. But it directly takes from your RAM, and then through the memory controller it goes to the FPGA, and the reverse is also applicable. It goes like this to your memory controller and then back to your RAM. This is actually an advanced FPGA concept. There are types of communications that the FPGA does with the system, but I'm giving it to you in a short span because we're out of time right now. If you want, I'm also taking a session on the 20th. I can give you a much more detailed explanation of this if you wanted to. Okay. I hope that's
Raghavan,
answered your
you
question.
can share
Yeah.
your mail ID in the chat box so that for any other
Yes, sure.
queries they can contact you.